Thank you very much. Hello, everyone. Hello, everyone online. I assume I just press next to go to the next one. My name is Marc North. I am doing my PhD at Durham University. I'm also a senior developer at MethodGrid, which is a project and knowledge management SaaS platform. And yeah, that's definitely what you're saying. This follows on quite nicely from some of the talks we've heard earlier today. In the keynote this morning, we heard about using LLMs to generate models, and I'm going to be talking about using models as input to LLMs to generate code. Just to orient ourselves in the software engineering lifecycle, I'm a developer. I live down here. And increasingly these days, as I think with a lot of developers at MethodGrid, we are using AI to assist us write our code. And what we are finding is sometimes it's a huge boost to developer productivity. You know, you're writing some code and it gives you exactly what you want, and it's like it's read your mind and it's magic. But there are other times when they're a bit of a distraction and they give you some code that is usually syntactically correct but doesn't quite do what you want. And usually what we found is when the code isn't doing what you want it to do, usually where it falls down is in its knowledge of the domain you're working on and the wider context of the structure of your application and things like that. So naturally this raises the question, what if we give the LLM some knowledge about our domain and about our wider structure of our system? Is this what I'm going to be talking about? I'm going to talk about two things. Firstly, as I said, using models as input to LLMs to generate code. I'm going to step through an example and see how the code that's generated differs when we give it these models and when we don't. And then secondly, going to have a look at the innards of an LLM as it's generating this code to see what information we can glean from it and try to create some mappings directly between specific parts of the models and specific parts of our code that it generates. So this is what MethodGrid looks like. This is the example that I'm going to show you the implementation of in the code. Very briefly, these are stages. This is a project. Within a project, you have stages. Within stages, you have these tasks. And so the code I'm going to show you is quite simple. It's just allowing people to change the status of a task. So you've got a task, you've assigned to it, you can set it to complete or in progress, on hold, whatever. And just very quickly, this is a sequence diagram of the feature I'm going to show you the code for. So all it does very quickly, checks if the stage is locked. If a stage is locked, you're not allowed to change the status of any tasks in it. Then checks the permissions to see if the person trying to change the status is actually allowed to. And if those two conditions are fine, changes the status and then dispatches this event to an event bus and a bunch of other stuff happens. So this is going to be our first attempt, and it's going to be a very simple, sort of naive attempt. We've got a large language model. In this case, this was done with the 34 billion version of CodeLlama, which is one of the open source ones. But basically all of this, the story I'm about to tell happens regardless of what model you use, and this all happens with ChatGPT or any of the other models as well. So we say to it, write a Python method called update status in a class called service status. And that's literally the entire input to the LLM. And this is the code we get. And this is the sort of code I was talking about when I said, you know, it doesn't quite do what you want it to do. It's syntactically correct, but it's rubbish. It's not at all doing what we want it to do. It's not checking if a stage is locked. It's not checking any permissions. It's not using the language of our domain. It's not talking about tasks or stages. It's just using this really generic entity idea, which in its defense, it doesn't know about any of those things. So why would it use any of that language? So we're going to have a second attempt. And this time, we're going to actually give it that sequence diagram. We're going to ask it to generate the code again, but we're going to give it the sequence diagram. And it being a language model, when I say we're giving it the diagram, what I mean is we're giving it, in this case, UML text that was used to generate the diagram. It'd be an interesting sort of future work to have sort of a multimodal model that can actually understand the image directly, but for now, we're just giving it the text. So we give it the sequence diagram plus the initial prompt, you know, generate a method, etc., etc. And this time, this is the code we get. And you can start to see that it is actually following the logic of the sequence diagram. It is checking to see if the stage is locked. It is checking the permissions. It's dispatching this event to the event bus at the bottom. And this is pretty encouraging. This is not a fine-tuned model that has been fine-tuned to understand these models. This is just, off-the-shelf code llama. But it's not quite there. And there's a few issues. One, where's it getting this from? Where's it getting this from? Where's it getting this from? It's just kind of plucking these things out as global variables because it doesn't know where they come from. But it's an improvement. It's a massive improvement on what it did the first time. So the next step, because the issue here is it doesn't know about the relationships between any of these things. It doesn't know where to get these different entities from. It doesn't understand the relationship between a task and a stage. So we're going to have a third attempt. And this time we're going to give it a class diagram as well, where we explain to it what the relationship between all these different things are. Just very quickly, we can see that a task belongs to a stage. This is the method. So yeah, the class we're actually implementing. It has a parent class that has access to this event bus and this member variable. And it has it knows that this should throw an exception, all this sort of stuff. And again, when I say we give it the class diagram, what I mean is we give it this text. So we're going to do the same thing again. This time, we're going to give it the class diagram, the sequence diagram, and the same initial prompt. We're going to ask it to write the method for us, and this is what it comes back with. And this is very good. You can see it's understood where the relationships between the different things are. This self.member, it knows that it has access to that because it was in the class diagram. We told it that this method throws exceptions, so it's thrown an exception rather than just doing the if statement, which is what it was doing before. It understands how to access the event bus. It's using the actual constructor interface from the class diagram, and it's got the correct arguments, it's got them in the correct order. And there's a couple of minor things that aren't quite there, but as a developer, the first example we had, I'd have just thrown that away and started writing the code myself manually because it was useless. This is 90% of the way there. In terms of the point LLMs are at, for now at least, they're not replacing developers. They're a productivity tool for developers, and this has got me 90% of the way there and have saved me a ton of time. Just before I go on to the next bit. So this by itself, I think, is a very interesting thing. We saw earlier today that these LLMs understand domain models enough to generate them. Well, they also understand them well enough to use them to write code, and write code that conforms to those models. And this by itself is, I think, very interesting and very encouraging. So this is the end of the first half of what I want to talk about. Second half, I'm going to dive into some of the internals of what's going on inside the LLM. I'm conscious of time, so tell me when I've got like 2 minutes left. So very quickly, neural network explainability. I've shown an image here just because this sort of thing is a lot easier to visualize when we're talking about images rather than text. And this is a picture taken from a Smooth grad paper, which was written by Google. And the idea here is this is an image classification network. And what it's showing you is when this model is classifying this image, what you do is you differentiate the output, in this case, the classification prediction, with respect to each of the inputs in this case being the pixels of the image. And based on those gradients, you can start to get an idea of what the model is looking at when it makes its decision. And we can do exactly the same thing with text data. It's slightly more complicated because text doesn't really lend itself to doing this quite as well, but we can still do it. And so this is what we're going to do with the code we've just seen. So this is the input we had, write a Python method, etc., plus the sequence diagram, plus the class diagram. This at the top, which is slightly cut off, is the code that it output. Because these LLMs are sequential, you run through the model once, you get the first output, you then have to run through the model a second time to get the second output. So this is we're only looking at the first forward pass through the network here. And what we're going to do is we're going to differentiate this output model, this output token, with respect to this first output token. There's a bit of normalization that goes on, which I'm not going to go into the details of. And when we do that for the example we've just seen, we get this number. The same thing for the second one, gradient of that with respect to that, we get that. We do it for the third, and so on, until we end up with, and this is all just for the first output token, we end up with this vector of about 400 elements, one element per input token. What we can do with that, we can draw a nice little diagram. And this diagram shows this is the inputs from the class diagram, and the strength of the highlight is essentially how big the gradient is for this output token with respect to each bit of this input token. What this essentially means is, what was our LLM looking at when it generated this output token? And same with the sequence diagram, which bits of the sequence diagram was the LLM looking at when it generated that bit of the output. We can do that for the second output, the word status, and then the third output, and so on, and so on, and so on. And you can start to see the gradients kind of shift around the input. It's looking at different things when it's generating different output tokens. And so far, nothing hugely interesting has happened. You know, they're all fairly low gradients. They're all kind of spread out. And there's a simple reason for that, is because all we have generated so far is the name of the method and the name of the class. And the LLM doesn't need either of these diagrams for that information because it was all in the prompt. Where things start to get slightly more interesting is when we look a bit further down in the code. So remember this self.member in the first two examples, it got it wrong because it didn't understand the relationships. It didn't know where it had access to this member variable. But now that it has access it, what we would expect is that we'd have quite a strong gradient on the bit of the class diagram that tells it about where it can access this member variable from. And that is exactly what happens. So these are the gradients for when it was generating this member output token. And you can see it's got very strong gradient at exactly the point where we would expect the class diagram where it tells it where this member variable comes from. Same thing with the sequence diagram. The strongest gradient is at the relevant part where it's telling it about the signature of this method. We can do this for any part of the code. So this update status bit, again, strongest gradient in the class diagram is the relevant part where it tells it about that method. And again, in the sequence diagram, strongest gradient is where the sequence diagram is the relevant part of the sequence diagram. Another quick example, the event bus, again, the strongest gradients with the relevant part of each of the two diagrams. And where I think this is potentially interesting in the future, potential use cases. So as a developer, I'm spend my life staring at a screen, staring at my IDE. And there's already a bunch of tools that already exist for if I want to know more about where my code came from. So if I have Git integration into my IDE, if I want to know where a certain line of code came from, I can ask my IDE and it'll tell me who wrote the code, it'll tell me when they wrote it. If they wrote a good commit message, it'll tell me why they wrote it. And I think in the future, if we start having these gradients, we can build a mapping from our domain models to our code. Well, we can start to integrate this information into our IDEs as well. So as a developer, I look at this bit of code and I say, I want to know where did this come from? If this was generated using an LLM, which parts of our domain model did the LLM use when it generated this bit of code? And it can tell me, because if we save those mappings, those gradients, and we have that as part of our version control system, it'll be able to tell me what the LLM was looking at when it generated this bit of the code. And we can do that with any bit of the code. And again, this members bit before, there were 3 different places that had strong gradients. So it'll be able to tell us, here's the 3 different bits we're looking at. Other interesting thing, these mappings go both ways. So we can look at each bit of code and say which bit of the models we used to generate this bit of code. We can also go the other way. We can point to a bit of our model and we can say which bits of code had strong gradients for this bit, and we can see those are the bits with the strongest gradients. So we can start to query in both directions, both our code to say where did this come from, and similarly our models, which bits of the code came from this. Another potential use case for this sort of thing, let's say in the future we want to update one of our models. So this was part of the service class that had this member variable on. In the future, let's say I want to change it to a more abstract concept of a principal rather than member. Well, in my version control, if I have these mappings saved, I can say which bits of my code are likely to be affected by that change, and it can tell me because it knows which bits of the code were generated by this model. And I'm aware with a lot of this, I'm getting quite a bit into the future. Wouldn't it be good if? But yeah, wouldn't it be good if? So some challenges and some potential future work for this. One is computation speed. In the example I showed you, doing a forward pass through the network. So the example I showed you uses smooth grad, where you actually do a backwards pass through the network multiple times to calculate the gradients. So it is significantly slower to calculate these gradients than it is to just get the output. So that's one challenge. The other is scaling, and I know this has been talked about before earlier today when we've been talking about AI. How well do these things scale? You know, if you have 2 sequence diagrams generating one function, it seems to work pretty well. What if you've got hundreds or thousands of inputs and you're generating a huge enterprise level code base? How well does that work? Potential future work is fine tuning models specifically for this sort of thing, or to understand domain models generally. And with these open source models that exist, that is definitely something that can be done now, albeit it takes some pretty good hardware to do it. And again, this is getting into the future again, but I think a reasonable question to ask is, can we do this for other stages of software engineering? So let's say we start off with our requirements and we use our requirements and an LLM to generate some tests, or we use that to generate some domain models and we use them to generate code and we use them to, whatever else. Can we step through the entire software cycle in a continuous way and say which bits of our end code or our tests came from this bit of our model or came from this requirement? And similarly, if we want to update in the future, if our requirement changes, can we step through and say, based on what we know of these gradients, what impact will this have on our entire system? Again, getting into the future, but it's potentially the direction things are going. Neural network explainability is, there's a lot of work to be done. It's slightly embarrassing how little we know about how LLMs work, given how much they get used these days. I think if we improve these sorts of explainability techniques, this sort of thing becomes more possible. Education, we've talked about before, teaching students to code. Do they need to be using LLMs more in education? IDE integration, I've just mentioned on. I'm conscious of time, which is why I'm rushing through this at the end. Some key points. LLMs understand domain models. They don't need fine tuning, but they'd probably get better with fine tuning. This is something can be used already. Secondly, we can create these mappings using the internals of an LLM between different levels of abstraction within software engineering lifecycle. And thirdly, neural network explainability has practical applications. I think it tends to mostly be talked about in terms of trust and things like that, which is important, but maybe there's some practical applications as well. Pending questions, that's all from me. Thank you very much.